enough memory on my stick to be able to get the recording done, and we can go from there. So, I think I've probably had the most email on the problem where you're given 2.9979, whatever number of digits afterwards, and you're told that it's times 10 to the 8, and it asks you to put it into 3 significant figures. And all of you go, okay, I can do that. I'm going to put it in 3 significant figures, and if I'm writing it out on a piece of paper, I'm going to write it like that. You type that into WebAssign, and it goes, eh.
Can you focus the...
Sure.
Thank you.
Maybe. Is that better?
Yes, ma'am.
It looks focused on this screen. It looks focused on my confidence monitor. And then so it goes, incorrect. And you're going, I think I've done this before. I'm pretty sure that's correct. WebAssign wants you to type it in like this. And when you type it in like that, it's a much happier camera. Okay, that's WebAssign's shortcut. And if you get into a problem where it's a formatting thing, holler. Really holler, because don't waste your tries on trying to fight the formatting. You don't want to really do that. So you definitely want to kind of keep that going. Okay, folks, I hate to do this to you on the chat.
I have a question. Is the 8 an exponent of the E, or is it just multiplied by the E?
Well, this E means, this E in WebAssign means times 10, and the 8 is the exponent.
Yeah, but like when we're writing it as the answer, do we have to put it as the exponent of the E, or just next to the E?
Just next to the E.
Okay, thank you.
Okay, I hate to do it to you guys, but so those of you who are online, you're going to have to speak up if you have a question today, because I'm getting an echo and a reverberation through my phone. And there was no way I could shut off my phone even though I've got it muted. So I'm going to have to sign out of the Zoom meeting on my phone. On my laptop, I can join and tell them I'm going to dial in and never dial in. On my phone, I can't do that. So, but yeah, this E, so that's how you're going to write it into the problem. Okay, so for 2 equations, 2 unknowns. There was a warm-up problem or in a pre-work problem that looked pretty close to something like this. It gave you a 36t minus 28 is equal to 0. And then I had 54x plus 36t squared is equal to 25. And I wanted to solve for t, and I want to solve for x. These are 2 independent equations. So you get 2 equations, 2 unknowns. I could have something that looks like this. So let's do one that looks like this. 36t minus 24x is equal to 0. And then I get 54x plus 36t squared is equal to 25. Still 2 equations, 2 unknowns. When you way back, now depending on when you took college algebra, which could have been a year ago, it could have been 10 years ago, could have been 15 years ago, but depending on when you took college algebra, they actually spend a whole lot of time giving you multiple ways to do this. And we're going to show you some mathematical tricks in a little while, but the simplest way to do it is solve for one and use its substitution. And that's the brute force method. That method always will work, but it just may take you a heck of a lot of paper to get there. Okay? So we're going to do the brute force method, and what I'm going to do is I'm going to solve this one for t. Now actually, because x is only to a single digit, there's a single power, let's solve it for x. So I'm going to solve this for x. And I'm going to get 36t is equal to 24x. X is going to be 36t divided by 24. And because I don't like carrying around fractions, okay, since I don't like carrying around fractions, I'm going to go ahead and do that in degrees. I'm going to go ahead and do my 36 divided by 24, and that's going to give me 1.5t. So I'm going to go ahead and substitute that in for x. So I'm going to get 54 times 1.5t plus 36t squared is equal to 25. So 54 times 1.5, just clean it up. This gives me 81t plus 36t squared is equal to 25. Now I just have a quadratic equation and I can solve for t. So that's the brute force substitution method.
Can you scoot the paper up a little bit?
Maybe. If this calculator will let me. There we go. So that's a mathematics thing that we've got. And like I said, throughout the semester, we'll show you a couple other tricks that we use that make it simpler. But the brute force method always works. Brute force method always going to work. Everybody good? Cool? All right. So, one of the problems we did on Wednesday is we had a mountain, and now that you guys have actually gotten into your homework, you probably recognize this problem now. And on Wednesday you didn't because several of you hadn't gotten into your homework. But I got a mountain and we want to find the height of the mountain. And our person starts out over here and measures an angle. And one of the problems is we don't know the distance to the mountain, and we're just going to call that d. Now the person is going to move forward and is going to get closer to the mountain, and that distance is x. And we get a new angle, theta. We know what is known is theta, or phi, x, and theta. We don't know d, and we don't know h, so these are our unknowns. D and H. Well, let's take this first triangle first. This first one is that the tangent of phi is going to equal h over d. This value is known because we were given that in the problem. So we can figure out that that's just a number that we know. So then if I do the tangent of theta, that's h, except now this part of my triangle is d minus x. So now I can put d minus x. This is known. What I don't know is h, and I don't know d. If I'm trying to solve for h, I probably want to substitute what d is so that I can get this in terms of h. But I have equation 1, and I have equation 2. Two equations, two unknowns. I can use the brute force method to do the substitution and then go ahead and solve the problem. And since homework is due at 11 o'clock tonight, I am not going to solve it for you in class. But that should get you started if you haven't already figured it out. Okay? Making sense? of you struggled with it. It's making a lot more sense now. Okay. So, the book gives you a problem-solving strategy. So let's kind of go over a problem-solving strategy, okay? Anytime you got the problem, is the first thing you want to do is read the problem. Okay, first thing you want to do is read your problem. Second thing I recommend is draw your picture. Because you really need to know what's physically happening in your situation. Okay? And at that point, you want to look at what do you know, and then what are you trying to find?
It's kind of hard to see it.
Oh, it is. Let's see if I can do this. Is that better? It's doing weird things today. So what are you, so read the problem, draw the picture, what do you know, and what are you trying to find? It's really got a bad glare in here. So we can focus a little better. There we go. I'm just going to have to move my paper a little more. So, just like what we did here, what did we know? What don't we know? So, we've drawn, this is the person's on the mountainside. The person wants to measure the mountain, standing next to far away. It does, measures the angle, walks towards the mountain a certain distance. So drawing the picture helps us figure out the problem that we're working with. We know what we know and unknown, and then it tells you either figure out your equations or select equations. Depending on where we are and dealing with, you may have a toolbox. And that's what we're going to start doing today, is we're going to start developing a toolbox. Especially for kinematics. Unfortunately, as we get further into the semester, you're not going to have one-size-fits-all equations. Just like there was not a one-size-fits-all equation for this problem. You're going to actually have to develop the equations that you're going to need. That's why it says figure out the equations. Then what the book will tell you, the book will tell you to algebraically solve can't spell this morning. For what you're looking for. So if I were doing that, what it would say is I'm going to leave the tangent of phi in there, and I'm going to leave the tangent of theta in there, and I'm going to go ahead and solve for h algebraically. That's what the book's problem-solving strategy is going to have you do. Sometimes that makes sense. Sometimes that doesn't make sense. Like, if I've got this variable in here, it may be confusing to you. If I go ahead and put a number in here, it makes it a little more straightforward for you. You're going to have to know what best works for you. There are a lot of times that I go ahead and plug in my numbers just to make it a little more obvious as to how I want to solve the problem. Sometimes I want to go ahead and leave it in terms of the variables. So this step is going to be kind of a dependent step for you. And then they say plug in the numbers and then check to make sure it seems reasonable. So these two steps right there kind of go together, and it's going to be whatever is best for the situation or whatever is best for you. The reason they tell you to go ahead and algebraically solve for it is that I may use that solution again and again and again, and it makes it easy to change the numbers. If I plugged in numbers earlier, I have to go back to the step where I plugged in numbers and do it again. So it just depends on your particular situation. So that's the problem-solving strategy that our book gives us. Okay, how are we doing? Doing okay? Anybody, any questions? Everybody doing all right over there in Tonkawa? Everybody doing okay on the phone? All right. One other thing, I have not assigned Pivot Interactives. You will probably see a Pivot Interactive get assigned over the weekend, and you will probably see information about McGraw-Hill before next Wednesday. I got all the sign-in stuff and everything to force out, and I'm going to play with it over the weekend. So you'll start seeing some of those virtual simulation laboratory things start coming out. But no, Pivot Interactives, nothing's been due in Pivot Interactives yet. Okay? All right, so I think where we were, if I remember right, is we had started talking about one-dimensional motion, and we had done my little clown car, and we had gone up and back across the number lines, right? I think that's about where we were. Does it look familiar to people? Okay. And we had talked about distance traveled. And we talked about displacement. And we had said that distance traveled is a number, but displacement is a vector. And we started talking about vectors. Now, from the previous general physics classes, I had done them a terrible disservice until I discovered this last fall. Last fall, I discovered that your algebra textbook, or the algebra textbook that they utilize here, never once mentions the word vector. Never once mentions the word vector. But you've done those problems, like what we have been doing already, where I have this is an x and a y, and you've done the problem where this is an r and a theta. All that is are vectors. Okay? Those are all that is vectors. They just never gave you this word. So it's a brand new word. It's a nice new vocabulary word. The thing about vectors are they have magnitude and direction. So while we're in this chapter and we're only talking about going this way, or we may be talking about going up and down, we're only traveling in one direction, we still have a positive and a negative direction. For those of you who've already experienced the laboratory, you're walking toward the detector, which would be a negative because of the way the detector works, or you're walking away from the detector, which would be a positive. You're moving further and further away. If this is your detector, you're moving further and further away. That's in the positive direction. As you move closer, you're getting to the negative direction. So if I'm doing this, this is just a positive and a negative, and it's telling me which way am I going. That is my direction. So if we think about that for a second, we can just kind of think about it. What happens is, so I've got some sort of city map here, and we've played with these kinds of problems probably back in 3rd and 4th grade. We played with the problems. They drew you a city, little city map. And they said that, we'll use Juanita. Although I have a friend, her name is Laura Pence. She's changing her name this week to, I am not a hurricane and I am not related to Mike Pence. Yeah, she's been a stitch this week. I'm not a hurricane and I'm not related to Pence. So Juanita over here, Juanita's going to walk 3 blocks this way. Then she's gonna walk 2 blocks up, and then she's gonna remember that she forgot something, and so she's gonna dash back and go pick it up over here, and she ends up over here to get whatever it is she was supposed to. Now, distance traveled would be the whole blue line. Displacement is going to be this line right here. This is displacement. Now, we can go ahead and do this, and we can describe this position, but I can also do a vector that describes that position. So we can get this vector. So my vector has a starting point, a stopping point. The length of my vector is its magnitude. And I can add vectors. I can add vectors head to tail. So while we're still right now just dealing with positives and negatives, we're going to really quickly go into dimensions. And we're going to have this vector. So it's important to start looking at this in terms of what's a vector and what's not. Because displacement is a vector. And we usually represent a vector with a notation that looks like this. We usually represent that. And we usually start saying, if I have a unit vector, the unit vector means the magnitude is equal to 1. So it has a magnitude equal to 1. And if it's in the x direction, we're going to use an I hat with a caret. And if it's in the y direction, we're going to use a j hat with a caret. And if it happens to be in the z direction, that's going to be a k hat. And you folks have likely seen this before in algebra, but they never told you why we use an I hat, j hat, and a k hat. It was more about how do I describe this thing here to be able to describe this point here. So these mean unit vectors. They have a magnitude of 1, and they're going to tell us direction. And the big thing is for distance traveled, we get displacement, and displacement is a vector. So if we define displacement mathematically, we can use, I'm going to go ahead and use the word for right now. Displacement is going to be my change, and we're going to use x for right now. And that is x final minus x initial, and we actually define it that way. And I think that's where we got at the end of the day on Wednesday. I think that's where we got at the end of the day on Wednesday. And my units for this is going to be in meters, or feet, or centimeters. It's some unit of length. But since we're using SI units, we're going to use meters. All right. Now, when I am traveling in the car, not only do I have when I'm moving and I'm in motion, not only am I having a displacement, but I have this time situation, right? And we've all done the problem that looks like this. Joey traveled, at 35 miles per hour for 35 minutes. How far did he go? Just about everybody can do that problem here, right? So let's do it. So I'm going to do 35 miles per hour. Uh-oh, I'm in 35 minutes, right? Shoot, but I know I've got to have time up here, so it's going to be times 35 minutes, but I got to get minutes in the right units, and we know there are 60 minutes to 1 hour. So that's going to give me my value. And a lot of times, to make my life simple or to keep me straight, I go ahead and do my conversion first. I can do it all as one line, but I'm going to keep my conversion first. So I'm going to do my 35 divided by 60, and it's 0.58. And if we want to keep significant figures, this 60 is a infinite number of significant figures, so it's not going to control my significant figures. I'm going to end up in 2 significant figures. Rule of thumb is you can carry an extra significant figure for your intermediate calculation, but it's going to be 0.58, and I'm going to multiply that by 35, and we find out that he traveled 20.4 as an intermediate miles, because minutes will cancel, hours will cancel, and I get 20.4 miles, but what I'm going to report is 20 miles because that's 2 significant figures, and I got to use my little decimal point to show that that's a real value. But we've been doing those problems forever. But as soon as you come to physics class, you're going, oh, that's not right. Because you're in physics class and you think it's got to be harder than that. No. Now, that's distance traveled, though. Okay? This is distance traveled. And what we don't know is displacement. Okay? We don't know displacement because we don't have enough information to give you displacement. Now, distance traveled and displacement could be the same thing. But we just don't know from the information that was given. But we want to look at this 35 miles per hour, right? Because we know that that could be a speed or a velocity. Speed is distance traveled divided by the time. And we can look at it as an instantaneous value as well, but that's what speed is. But velocity is something a little different. Velocity is a vector, and it's defined as the change in displacement divided by the change in time. And we usually represent it with a V. And I've got my D for displacement divided by time, except we usually end up doing this as an X divided by time. So my general equation that we usually see written somewhere is my distance is velocity times time, where that's a vector and that's a vector. Now, we're going to complicate things a little bit. This equation only works when there's no acceleration. We'll talk about acceleration in a little bit, but this equation only works when there's no acceleration. But let's also look at the units here. So if I'm looking at units, this is in meters and this is in seconds, so the units are in meters per second. So we can do a graph. And we can do a position versus time graph. Positions in meters, times in seconds. And we're going to describe the motion of a car. Okay? And we're gonna start at 1, and we're gonna do 1 mile, and we're gonna do, oh, this is time. So we're gonna do, oh, let's do it. Oh, yeah, let's go ahead and do it this way. This will be 30 minutes. Oh, I got it in seconds. Oh. That's why I don't like doing problems off the top of my head. So if I'm in seconds, we'll just do 1 second, 2 seconds, 3 seconds, 4 seconds. And so this will be a toy car instead of an actual car. And this will be 1 meter, 2 meters, 3 meters. So we're going to play on the, it's like rolling cars across the floor. So we're going to go, the little car is going to go from 0 to 2 meters in about 2 seconds. Then it's going to stop. And we're going to let it sit there. And then we're going to have the car move only 1 meter back towards there. Now, if it's a straight line, this is going to be a constant velocity. Straight line is going to tell me a constant velocity on a position versus time graph. We can calculate that constant velocity by looking at the slope. Okay, let's remember the old rise over run thing. The rise is going to be, in this case, depending on where I'm at, the rise is going to be, we'll do the whole line. So the final position was 2, the initial position was 0, the final time was 2, the initial one was 0, and this is the run part. And so this is going to be 2 divided by 2, and this is meters per second. This is going to give me 1 meter per second. So I can determine the constant velocity off of my graph. I can use the slope to determine the constant. So let's do something real quick. The general equation for a line is y is equal to mx plus b. Right? That's my general equation for a line. Now, if I'm doing it off of a graph here, we're going to represent position with an x. We're going to represent time with a t. This y is my y-axis, so this is x. And this is my x-axis, so that's t. Our y-intercept was 0, right? My y-intercept was 0, so I've got a plus 0. There's my slope, and we've shown that that slope is a v. So this can actually, we can actually do this as our equation of our line is our x is equal to the velocity times time plus my initial position wherever my initial position was. So my graph here really describes my motion, and I've made a link to that through my equation out there. So you'll, and I think in your chapter 2 homework, it's going to give you a graph, and you're going to have to actually write the equation for it. You're going to have to pull the information off of the graph to give you what the velocity does. So I can do another position versus time graph, okay? I can do another position versus time graph, and this time I'm not going to do, and the position versus time might do like something like this. Okay, this is still a position versus time graph. Uh-oh, my pen is dying. That's going to make me an unhappy camper. So this is time, okay? So I still have a position versus time graph. And I can look at this graph and we can look at a few things. looks like since that's a straight line, during this part of the motion, that's a constant. But then during the rest of this stuff, not so much. I've got something else that's going on. But we all know, think about when I'm in the car, right? I'm in the car and I'm driving along the car and I can speed up, slow down, do all kinds of stuff. But I always know what my instantaneous velocity is by looking at the speedometer. And somewhere along the line in college algebra, you learned how to take an instantaneous value on a curve by drawing a tangent to the curve. And you could take the slope of that line, good old rise over run, and this would give you something that's an instantaneous, and this happens to be an instantaneous velocity on my curve. So all that stuff you learned in math actually has physical meaning. And for those of you who may go on to calculus, what we're saying is this instantaneous velocity is the limit of my change in position with respect to time as time approaches 0. Because what we're doing is we're looking at a narrower and narrower and narrower and narrower part of this in order to come up with that instantaneous velocity. So we can have an instantaneous velocity. Still in meters per second. Still looking at how things are going. Now, if I'm on a velocity versus time graph, so I got a velocity versus time graph. And we're going along here, and then we go, well, I'm going to do this, and then I'm going to go along here, and then I'm going to go really, really quickly out here to 0. I can read my instantaneous velocity at any time just by looking at the value that's on my curve. Okay, so if I'm looking for the instantaneous velocity, we'll go ahead and give ourselves some numbers. We're going to say that this is 1, and we're going to say that this is 2, and we're going to say that this is at 1 second, and we're going to do this at 2 seconds, and this is going to be at 4 seconds, and this is going to be at 5 seconds. So I've got a 3 seconds kind of halfway in between. Okay. Yeah, it's a little off here, but we'll go with it. So my instantaneous velocity at 1 second, and this is going to be in meters per second. So my instantaneous velocity at 1 second is 1 meter per second because I can read it directly off the graph. My instantaneous velocity at 3 seconds is going to be 2 meters per second. My instantaneous velocity at 5 seconds is going to be 0 meters per second. But what this is telling me is I'm on cruise control for the first second. Then I'm going to do something, which we're going to call acceleration here in just a second. Then I can accelerate at a constant because I got a straight line. It's a constant acceleration. I can accelerate from 1 meter per second to 2 meters per second. Then I'm going to go hit the cruise control again and stay at 2 meters per second for a while. And then I'm going to hit the brakes over the next second to stop. So this is going to be called a deceleration, and this is an acceleration because my deceleration is going in the opposite direction. So we're going to define, so we've defined velocity, kind of just refresh here, velocity is my change in displacement over the change in time. But acceleration is going to be a change in velocity with respect to time. Velocity is going to be in meters per second. This is seconds, so I get meters per second times 1 over seconds gives me meters per second squared. This is a vector. This is a vector. And if I write this out in terms of terms, I get acceleration is equal to velocity final minus velocity initial divided by time and if I multiply both sides by time, I get velocity final. I'm going to just do a real quick rearrangement. I get velocity final is velocity initial minus acceleration times time, and this becomes another tool in my toolkit. That just becomes another tool in my toolkit. Now, this only works if we have constant acceleration or something we call uniform acceleration. And lucky for you, we don't play in General Physics 1 with an acceleration that's not constant. We don't play that game to you guys. We aren't that mean, cruel, and wicked. Although I am mean, cruel, and wicked. I'm just a fair, mean, cruel, and wicked. My children will tell you that. And my grandchildren will say that now too. So now we've got another tool in the toolbox. So, and normally we would write it with our little vectors over the top. But right now we're in one-dimensional motion, so this makes life a little easier. So I could go through all the gory details and derive the equation, if you've got that in your book. And for most of you, that would be like taking a needle and poking your eye out, right? You know, you guys love seeing derived equations, right? Because I could do it that way. Just totally love it. Or would you rather me just give you the equations? Speak up. Not that early. You guys have had your coffee.
I don't like coffee.
Okay, so we have one. So one of our equations is that my change in x is going to equal the velocity times time, and this is with no acceleration. I'm playing the cruise control game. We just have shown that velocity final is equal to velocity initial. Did I do that? I did do that, you guys. Guys, let me get away with that. That should be a plus, folks. Because A goes over here, we move this to the other side, that should be a plus sign. So I'm going to give you a chance to fix your nose. So we get this plus acceleration times time. Okay? This has got variables of the velocity, acceleration, and time. Notice there's no position in this equation. Okay? No position in this equation. I can play with it, and your book will show it, or if anybody really wants to see it, I can show you. But I can do a change in position is equal to my initial velocity times time plus 1/2 acceleration times time squared. Now, we're usually given this initial velocity. That's not something we're usually solving for, so this is kind of like a known. So this equation gives me position, acceleration, and time, has no velocity. And just because we like to do it and play with it, I'll get a fourth one. This gives me my velocity final squared is equal to my initial velocity squared plus 2 times the acceleration times my change in distance. And this one gives me velocity, acceleration, and position. So when somebody says, I don't know which equation to use, if I've written down my knowns and I'm looking at my unknowns for these problems, I'm looking at what variables are they giving me, and this right here is going to tell you which equation you're going to use. Because your problem may say, so we're going to do this little problem right here. I got my little stop sign, I got my little car, and my little car is going to go down the road 100 meters. We're starting with an initial velocity of 0. And we're finishing with a velocity of 20 meters per second. I want to know the acceleration. So let's look at our knowns. Our knowns, we know the initial velocity, that's equal to 0. We know our final velocity, that is 20 meters per second. We know I've got a position or distance, which is 100 meters, which is going to be my x. So I have, and we want to know A. This is my unknown. So I'm going to need an equation that has a velocity, position, and A.
4.
Yeah, it's going to be number 4. But these two require time, so that's not going to work. That's not going to work. So I'm going to use this one. So I'm going to go, okay, v squared final is equal to v initial squared plus 2a change in x. Well, my change in x I already know, so I can get rid of that change of, right? I want to know acceleration, so this comes into that part about when do you plug in your numbers. So first thing I'm going to do is this. Make my life a little easier. We know what our initial velocity is, so that's 0. So if I write all the gory steps, this now is 2ax. I'm solving for a, so I get v final squared divided by 2x gives me a. If I've done my arithmetic right. So now I plug in the numbers. I get 20 meters per second squared divided by 2 times 100 meters. Plug that into my calculator. 20 squared. If I turn my calculator on, there we go. 20 squared divided by 200 gives me 2, and we can do our unit analysis. I get meters squared divided by seconds squared, 1 over meters. Meters will cancel. I get meters per second squared. So my acceleration is 2 meters per second squared. Now, once I know acceleration, part B of the problem may ask me for time. It may ask me for time. Well, if I know acceleration, I could use equation 2 now because I've already figured out acceleration. And I can do that one. So v final is equal to, our initial was 0. So now I have acceleration times time. So that's just going to be v final divided by my acceleration is going to give me time, which is going to give me 20 meters per second divided by my 2 meters per second squared.
Can you pull down the paper?
Yeah, okay. So I get my meters will cancel, one of those seconds will cancel, so I'm actually in seconds, and this tells me it's going to be 10 seconds. Now, a lot of your problems will give you enough information that you don't necessarily have to do part A first. You may be able to do part B first, and that may make more sense for you. There's nothing that says you have to follow a problem in A, B, C, D order. Now, in this case, you kind of did, because you had to solve for acceleration first before you could solve for time. But it's not always the case that we have that. Not always the case that we have that. People getting it? Doing okay? Alright. Now, if there is one example in a textbook that you should spend a lot of time looking at, in our textbook, it's an example that says it's an exceptional throw for a rookie. We're going to see this a number of different ways. We're going to see it again when we get to two-dimensional motion. We're going to see this problem over and over again. So what we've got here is we've got a situation like this. I've got a building, and we can describe the motion. I can take a ball that looks like I'm taking it from the top of the building, and it's going to go straight up, and it's going to hit the top, and it's going to come straight back down, and it's going to just miss the building. And it's going to come down to the ground down here. Oh, I'm going to have to back out here. I drew my picture a little big, which means it's going to be a little fuzzy. I apologize. But you do have this example in your book. Okay? So even before we get started, we know a few things. And we know a few things, and the book is going to make the assumption that you know these things. First thing we know is what's the velocity at the very tippy top?
0.
The velocity at the very top is going to be 0 meters per second. Because at the instant it's at the very top, it's changing direction, and it's going to be 0 meters per second. So we know that. The other thing we know, because we've done it since we were little. In fact, we do it before we can even crawl. We do it even before we can really hold our heads up by ourselves. We start playing what I call the dropsy game. If I'm in the Y direction, we play the dropsy game. And it doesn't matter if I drop this pin, or this pin, or this marker, or this pin, or my calculator, a ball. What does matter is if I have a feather, because then I got air resistance, and that's a different situation. It's still going to be affected by an acceleration. Always going to be affected by that acceleration. And that acceleration is our lovely acceleration due to gravity. And that acceleration is g. It's going towards the center of the Earth. And we're going to play with g a lot. Okay, so I'm going to go ahead and focus a little bit. So we're going to cut off our picture here for just a little bit. So it's always g. And our book is going to tell you it's 9.8 meters per second squared.
Isn't it negative?
It is negative, but I've got an arrow showing you this direction. Okay? And the reason I'm using the arrow right now is because we can set up our problem, because sometimes we're just wanting to find the magnitude of something, or if I'm trying to solve for time, I may just want to go ahead and use it in the positive sense, but by drawing my arrow here, I'm showing you the direction. But usually it's a negative 9.8 meters per second squared. But I'm showing you that by the little arrow right now. We are going to measure this at least 3 times over the course of the semester. And you guys are going to find out that it really isn't 9.8 or 9.81. I think our book actually uses 9.81. It depends on which book you're using. That happens to be at the equator. In Tonkawa, America, and Enid America, I've done this now several years, and we usually get something on the order of 9.79. And if you use the little gravity calculator app on the internet, which is pretty cool, it's going to give you about the same for our latitude and longitude. But the 9.81 meters per second squared that we use as a standard is based off of the equator. Right? So that, or if I'm doing it in English units, it's 32 feet per second squared. And your problem will never tell you that. And then I am mean, cruel, and wicked, and you're likely to see on a quiz problem, what is the acceleration of a ball that's falling down? And I will still have somebody tell me I don't have enough information, I'm going, uh-oh. It's going to be what? 9.81 meters, at least the magnitude is 9.81 meters per second squared. So we are always, so these are 2 pieces of information that no matter what we're doing on this problem, we already know before we've even read the rest of the problem. Okay? And what we're going to do though, is we're going to toss the ball up with an initial velocity, and we're going to use an initial velocity of 3 meters per second. And then we usually are given something like, okay, as soon as the ball, because we don't have perfect reaction time, right? As soon as the ball comes back by the edge of the building, we're going to start the time, and we're told that to hit the bottom, so I'm just going to do this just to make it easier to have it all on my picture here so we don't have to scroll back and up. We're going to measure the time that it takes to hit down here, and we're going to show that that time is equal to, we'll be good, and we'll do 0.35 seconds.
Give me a second, I got a bloody nose.
Okay, no, I think you're right. So we actually have that, so this is the time from here to here that it takes to go down. Now this is why you draw your picture. Because now the questions that I can ask are, what was the maximum height? So I can ask, let's see, I want to use a red pen so we can see this. I might want to know this height. Okay? I might want to know this height. I might want to know this height. I might want to know the velocity when it hits the bottom here. Now here's the really cool part. Once I was told what my initial velocity is up here, I know what the velocity is at this point. The velocity at this point is going to be what?
The same as the initial.
It's same as the initial, except it's going to be negative at that point because it's going in the opposite direction. And then I could be mean, cruel, and wicked and want to know what the total time, which is going to be the time of this part plus the time of that part. So this problem right here, as we've set it up, allows us to do a whole lot of different things. So let's start with this part. this part here, we're told the time that it takes to go from here to here, and we want to solve for the height. We want to solve for the height. So we want to know what h3 is. So the first thing I know for this part of the problem, I know what my initial velocity is. So my initial velocity for that part of the problem is going to be a negative 3 meters per second. I know my time is 0.35 seconds. And I know my acceleration is, and in order to keep it, I want to make sure I have my directions carried out correctly. So I've got my 9.8 meters per second, not cubed, squared. And I want to find height 3. So on my little 3x5 card that I'm going to keep next to me while I'm working on my homework problems, I'm probably going to put this on there. Okay, probably going to put that on there. And I'm going to look at what I've got, information I have. And this time, equation 3 is probably what I'm going to use. Because I want to know the height, I have my initial velocity, I have my time, I have my acceleration. What I don't have is the height of the building. So we're going to do that. We're going to do h is equal to my initial velocity, which is 3 meters per second, times my time, which was 0.35 seconds. Cancel those out. That means I'm in meters. That's, life is really good. Plus 1/2 a negative 9.81 meters per second squared times my 0.35 seconds squared. Plug that into my calculator. This gives me negative 1.05 meters minus and if I plug it in my calculator right, I get 0.06 meters. So this becomes minus 1.65 meters. Now, this is one of those times that you got to be really careful in how WebAssign asks the question. Because if I put in the negative 1.65 meters and WebAssign's worded the question just right, it's really wanting the positive 1.6. It's maybe asking what's the height of the building, not how far did the ball fall. So how you ask the question is going to tell me whether or not I got to put the negative in there or not. Height of the building is 1.65 meters. The ball fell a negative 1.65 meters. So we can utilize a lot of the information, and so, like I said, go look at this one, this example in your book, because it's in your book. We'll play with it a little more on Wednesday. Now, according to my syllabus, we're supposed to have a test next week. But I'm not that mean, cruel, and wicked, because it's been a little more chaotic than things have been that I've wanted it to be. So you're likely to have a quiz next week, so that you guys at least get to see a quiz before you have a test. We'll still try to fit in 4 tests over the course of the semester. If we're lucky, we'll get them. If we're not, well, that's how, we'll go with 3. But just kind of keeping us all honest in that. So, because somebody's likely to ask me, hey, your syllabus said you have a test in week 3, we haven't seen a test yet. Let's get us down the road a little bit more. You don't want to test so far,
Did you say there was like an oral component next week?
No, the oral component, I will do an oral component